And I talked about UDP and I started TCP last class. So with TCP, the thing I wanted to recap was the use of sequence numbers. One of the things that you need to do to establish communication between two endpoints is synchronize on a set of sequence numbers that you're going to use to label the data going back and forth on that connection. So that's what this three-way handshake is doing. So sender A is like, hey, here's my sequence number A. I'll send that in a SYN packet to B. B is like, I got your sequence number. I ACK your A. And then I'm going to generate my own sequence number B and send that to you. And then after this three-way handshake, both of these endpoints have sequence numbers going in each direction. Now, after you do this, then the authentication, the connection level integrity is done based on your knowledge of the sequence numbers. So that's unfortunate because these things are 32-bit numbers. And as soon as someone either sees it or knows of it, then they could potentially get inside that connection and do things with it. And so this is a segue to TCP attacks and their countermeasures. So with TCP, it initially had no support for confidentiality. None of the payloads were encrypted. There was only data integrity via that checksum field in the header that I showed you last class. It's like a 16-bit checksum. So that's not much for data integrity. The source integrity, as I just mentioned, was your knowledge of the sequence numbers. And that will authenticate the fact that you are part of this connection, just knowledge of that. And as it turns out, there was very little support for making TCP implementations highly available. So this leads us to some of these attacks on TCP. The first one is this blind TCP spoofing attack. So the fact that sequence numbers are the only thing you really need to authenticate an endpoint, then if A and B are using predictable sequence numbers, the adversary is able to blindly spoof packets in that connection. So the adversary can write its own source IP address and destination IP address. And if it can guess the transport headers, it could pretend to be the other machine at any of the two endpoints on that connection. And this was the attack that was popularized by Kevin Mitnick. And I think we've mentioned him before in this class. He was a hacker that was very prolific in the 90s, the 80s and the 90s. So the way it worked was he attacked these R commands. And so RSH and RLogin were the predecessors to SSH. So they're similar to Telnet, but this was basically remote shell and remote login commands. And rather than having SSH keys that allow you to log in from your client to the server automatically, the R commands were like, we're going to authenticate you based on your IP address. If you are coming in on a particular IP address, we are going to allow you to say, hey, when I log in, say X and Y are part of the particle lab. And you're like, if you're on one particle lab machine, yeah, you should be able to log into the next one without having to enter your username and password. And so that's how, like, when I was an undergraduate, that's how we did things. We were like, in fact, I heavily used RSH and RLogin to get access to a whole cluster of, my school's machines. And so the idea is that, hey, in my file system, in my .rhost file, and this would be in your home directory, you would create this .rhost file. I'm going to put Y. So say I'm on X, and then I'm going to put Y as a trusted remote host. And so this denotes that I'm going to allow logins from Y without a password, without authentication. And that's what this command was doing. And then when I'm on Y and I do an rlogin of X, I immediately get my shell without actually punching in my username or password. And this is all done because my IP address or my machine name is sitting here in this .rhost file. Okay. The predictable initial sequence number of X is going to allow E to pretend to be Y without actually knowing Y's, or not, without seeing Y's packets going back and forth between X and Y. And so if E can pretend to be Y, E can get a session on X. And that's the attack that we're going to do. So this is the scenario. Say X has this predictable initial sequence number, and E wants to be able to spoof a connection from Y, and then basically create a command that appends itself to the .rhost file. So that's the idea. The first thing E needs to do is figure out what sequence number is going to be used between X and a potential connection from Y. So you're not going to be able to do a three-way handshake between Y and X and be able to get that sequence number. But if E makes an initial connection to X and gets the current sequence number, if the sequence numbers are predictable, then if Y were to connect to X, E would know what the next one would be used. And so initially, the TCP algorithm was start at 0 as your initial sequence number, and then the next connection uses 1, next connection uses 2, next connection uses 3. So that's what the implementation used to be in TCP. Okay, so E is going to say, well, what's the current sequence number that X is using? I'm going to find out what it is, and then I'm going to guess what a potential connection from Y would get as a sequence number. Now, in order for me to pretend to be Y, I had to blow Y off the face of the internet, right? Because Y, if I send a packet masquerading as Y, X is going to respond with a packet that gets sent to Y, and then Y is going to be like, hey, what the heck? That's not a connection I sent. Reset. So I need to make sure that Y doesn't tamper with my pretense, I guess is what I should say here. And so I'm going to just disable Y by sending just a massive packet stream at Y, blow Y off the internet. And then I'm going to blindly masquerade as Y by sending spoof segments pretending to be part of a connection. Now, because all of this stuff is predictable, it can pretend to legitimately be Y by rewriting the source IP addresses to Y, and then trick X into thinking this is a legitimate connection from Y. And then I can just send this command as a payload. I'm going to do an RSH to this machine X, pretending to be Y, and then I'm going to echo E at the end of .rhost. And then this is what will happen. I'll add myself to the end of rhosts. And now, because Y got blasted off the internet, the responses to this RSH command, which are actually going to be sent to Y, they get all dropped. So Y never sees these packets, and the command succeeds. So now you're in the .rhost of X. Now you can just log in as you would, as Y would have done. So that is the scenario. Are there any questions about what is happening there? And this is the problem with allowing people to write their own source IP addresses in their packets and having that connection setup be entirely predictable. Yeah.
So the ISI before was sequential starting at 0, basically now.
Now it has to be completely random, and it has to be not just pseudo-random, it has to be really random. And so they're like, this is in the late 90s to early 2000s. They were basically measuring the entropy of every operating system selection of initial sequence numbers. And then there's these beautiful graphs. Like I have the URL to this article where they're like, oh, OpenBSD. Yeah, they're actually using a hardware random number generator to generate the TCP random initial sequence number. And then these other systems are like using like these pseudo random number generators that have this nice, predictable pattern. So just because it looks random doesn't mean it is random. So we were talking about the cryptography thing. It's like, yeah, you could base 64 something and then say that looks random, but no, adversaries can predict that, and then you would get something like looks like this. Okay. So that is blind spoofing. You can do something very similar to reset TCP connections or to hijack an existing TCP connection. So the reset attack is really easy. You basically spoof. So assume you have a critical long-lived connection, like a BGP session between two critical routers, and they're exchanging routing information, and you want to pretend to break that routing link, like the adversary. The adversary is trying to like disrupt the network. And so what the adversary can do is try and spoof reset segments so that one endpoint of that BGP session believes that the other one got blown away, and then force this routing instability as the routes get recalculated throughout the network. And you can do this if you can guess the sequence, the correct sequence number of the connection blindly. So in this case, X and Y have this long-lived BGP session, and then the adversary E is just spoofing a reset from Y to X. And then you can actually brute force this, right? There are only so many sequence numbers. There's like, 4 billion sequence numbers. You can find a sequence number that'll work to reset this thing, and that's a problem. And that's basically what was happening in the back end for a while.
So once they reset it, do they predict where it's going to be routed?
So then these two routers are like, oh, that route no longer is up. That route is down. All those routes that particular router advertised need to be withdrawn because I've lost connectivity. And then if you do this persistently, then you can disrupt the topology on the back end.
Okay.
Yeah, you can't do this anymore, but like that was what was happening before, because your connection integrity was done based on sequence number knowledge, and that's not from a security standpoint, that's not really strong enough to prevent these kinds of things. The other thing you can do is if you're the person in the middle, you can just insert yourself into the path and then redo the sequence numbers going back and forth in order to modify data in both directions. And this is because the data integrity is only done via that checksum on the header, and you can patch that. If you're in the middle of the network, you can patch that so that actually looks okay, and there's no other data integrity on either side of a TCP connection to detect that kind of stuff. Yeah, you had another question.
How does that relate to like application level, like manipulating it, like with Burp Suite stuff?
So Burp Suite, this is something. Burp Suite is a proxy that is targeting web connections going back and forth and allows you to modify web connections going back and forth. And if you're just using regular HTTP, then or you're allowing Burp to terminate the HTTPS connection and then regenerate the plain text HTTP, you can modify stuff going back and forth. That is that's basically because the data integrity and the source integrity isn't on an end-to-end basis, right? And so this is why Burp works.
Is there a tool equivalent for TCP?
Yes, in fact, this is if you so Kevin McGrath is going to teach the network security class. He uses Scapy, or he wants to use Scapy, which is a way of rewriting packets. And then there's a Black Hat Python and a Black Hat Go book from No Starch Press, and that's what they do. They build packet proxies that allow you to rewrite things easily. You could actually do some of this stuff, I think, in IP tables as well. If you add particular, you would have to get into the IP tables chain. And we talked about IP tables last class, but that's how you could implement some things like that to programmatically send packets out. And that low-level packet hacking, that protocol hacking stuff is in the network security class. Well, it will be in the network security class after Kevin gets done with it. And that's what he's looking to do. So how do we get some countermeasures against this? Well, the first thing, which we already covered, I'm not going to cover it again, is TLS, right? That gets you confidentiality, source integrity, and data integrity on an end-to-end basis, unless, of course, you hijack the server's TLS certificate. So, like in Burp Suite, they forced the browser to accept the Burp Suite's TLS certificate in order to do the person in the middle attack on an HTTPS connection. That's basically what you have to do. So TLS is the sure way. For the connection level source integrity issue that we talked about with the blind spoofing, you do need a truly random initial sequence number so that that thing can't get guessed easily. The other thing, the third one, and this is for the BGP session reset one, is to basically establish cryptographic keys on either endpoint that you must be able to produce in order to reset a session. So rather than just using the sequence number, I need you to supply what was the agreed upon cryptographic key at session startup for me to believe that you actually want to reset this connection. So that's the other part of this. And this is using message authentication codes where you have exchanged the key at the beginning of the session. Yeah.
So the TCP protocol has a reset sequence.
A reset segment, yeah, that allows you to just reset that connection. And so these options say, well, even if that reset bit is set, I still want you to look at other parts of the payload. You have to supply the correct, signature check or message authentication code check in order for me to actually reset that session. And this is to prevent the blind reset session resets.
Why would they want to reset like legitimately?
If you do want to disassociate from that that peering point, then yeah, you would eventually want to tear it down. Yeah. Okay. So the next attack I want to talk about is the TCP SYN flooding attack. And like the name denotes, this is an availability attack on TCP. So this attack is trying to bomb the server off of the internet. And it's similar to that distributed denial of service attack. So the idea here is that you have an attacker, and then you have this server who's listening on a port for incoming connection. Say it's a web server listening on port 80, and it's just waiting for new connections to come in. So then what the attacker does is the attacker creates a socket on its own local machine and sends it using its client. So by setting the client port of its connection and sends this TCP SYN packet to the server. Now, rather than keeping the state around of this outgoing connection, the attacker has no intention of actually establishing a connection to the server. It's just sending these packets using a tool like Scapy or using a tool, other tools where they can programmatically send packets onto the internet without actually having to go through the operating system. And it's just like, I'm going to pretend to be a whole bunch of connection initiations, but I'm not going to actually keep connection state because I have no intention of establishing a connection. So I don't have to remember any of the sequence numbers I send. I'm just going to create this connection. The server needs to handle this packet legitimately though, right? Because it doesn't know whether this SYN packet is legitimate or not. And if it is legitimate, it has to basically create a new socket on itself to keep track of the client IP, the client port that was used, along with the other things. So this is it has to faithfully do the three-way handshake, assuming this is legitimate. But meanwhile, the attacker is like, you know what? I'm going to ignore this SYN-ACK. I don't want to create a connection with you. I just want you to create that state. And then I'm just going to keep on sending these packets to you until your operating system runs out of memory. And then I don't, like as an attacker, I don't run out of memory because I'm just sending packets, right? It's completely stateless on the attacker, and on the server has to keep all of these connections up. And usually on the server, the connection queue on a server is limited. Like you're basically based on the number of concurrent server processes to handle connections. Like on a web server, maybe you'll have eight processes handling incoming web connections. Maybe your backlog for this listen queue is like maybe 16 or maybe a couple dozen. And if I send a couple dozen of these things, I'll just fill up your backlog because I'm never going to respond with an ACK to allow you to accept the connection and serve it, which is what the server is trying to do. Yeah.
And then do all the SYN requests have to be from different IP addresses?
It could be from the same one, but if the server is filtering it, saying you're only allowed one per IP address, then you could rewrite the source IP address to be from anywhere on the internet, right? Like you could spoof the SYN packet. In fact, that's usually what's done. You would spoof the source address. So the incoming connection looks like it's from all sorts of different places, and then none of them will respond to a SYN-ACK. Okay, so that's the attack. And then you just keep on sending it until at the end, the server has no resources to handle legitimate clients. Yeah.
So the TCP, there's 4 tuples in the header where it's like it has the host port, host IP address, and then the destination IP and destination port.
It's kind of a 5-tuple because you also want the protocol like the TCP or UDP. It's considered a 5-tuple along with which transport protocol are you using?
Okay.
Yeah. So yeah, the two port, source port, destination port, source IP address, destination IP address, and then the protocol, TCP or UDP. And that just uniquely identifies a connection. And that's how like it's stored in operating system tables, as that's a unique connection. That 5-tuple denotes the unique connection.
So it wouldn't be possible to use manipulating the SYN bits as like a kind of like quasi proxy, because then you'd be modifying the host like port and IP, so then it's send the SYN-ACK to like a different address.
Yeah, so you can rewrite that SYN packet programmatically. Like you write a SCAPI program that says, randomly select my IP address, my source IP address, and then send it. And then you would rely on ingress filtering that we talked about earlier to try and filter that stuff out. So yeah, so this is why there's so many different little bits here in order to prevent this kind of thing. So that would be one thing that would help, is ingress filtering, so to prevent people from rewriting their source IP address. But here at Portland State, I could pretend to be anything from 131.252. That's a lot of machines. I can pretend to be part of. Okay. So there is a countermeasure, and this countermeasure is basically allowing you to keep the server to be constant state. And these are called SYN cookies. And so when a client comes with a SYN packet that the server is listening on, the server is not going to store any state. Instead, the acknowledgement and the sequence number used from the server back to the client is some hash of the initial source address, source port, destination address, and destination port, some time number, like an incremental time counter, and a server secret. And in this way, the server is basically signing a cookie without keeping track of this tuple. And when the ACK comes back, because this cookie is basically the sequence number, the ACK is going to ACK this sequence number, and then the server can recompute the cookie using this information. And if it matches the cookie that got echoed, then it recreates the connection and allocates the socket on the server. And so this is kind of a pattern that you can use to protect protocols on either end. Okay, so one of the things, so this is used to protect the server. This is also used to build mass scanning tools. So like Nmap, when Nmap does an Nmap operation, it's often keeping connections open for each one of the scans that it does. There's a tool called mass scan that puts cookies into the client initiation thing to keep track of which servers it's probed. Because the last thing you want to do as a scanning tool is to wait around for a server response. And so this is a stateless scanner that is using cookies in the reverse direction. I'm going to scan you using a cookie so that when I get an ACK, I'll know exactly how I scanned you to begin with. So this is just, these cookies can be switched around. I don't have a slide for this, but there are tools. So Nmap is the one we're using, but there's Zmap and MassScan that are basically stateless scanning tools. And they're using this, they're using this cookie approach to basically like scan a class B in like a minute, a class B network with 65,000 hosts. They can do that in a minute. And they just fire 65,000 packets and then wait for the responses, and they boom, they instantly get all of that scan done in a minute. So that's kind of an advanced tool that I'm gonna not have in this section. Okay, so the reason why I'm really covering TCP is because it's often used, like knowledge of TCP is necessary for you to scan the resources in a network, because almost all the services that are being run on the internet are using TCP. And so it's important to understand all the different ways that TCP can operate. So with TCP, TCP has a well-defined state machine that specifies how clients and servers operate when receiving certain packets in certain states. So this is a picture of the state machine that we're not really going to cover in detail, but I want you to see this part of the state machine. When you have a server that is listening, you'll see that when you get certain packets, you will generate certain responses. And this is a partial state machine. There are other packets that you can potentially get in each one of these states. But the idea is that because this is so well defined, you can determine just by sending a TCP implementation, a particular packet, whether or not that port is open or closed. So I am going to talk about different scans with TCP that leverage this. And the ones that I'm going to talk about are the ones that are in your labs. That TryHackMe Nmap room has a certain set of scans that it has you do. I'm going to just go through some of those, but realize that there are dozens of different types of scans that Nmap can do, not just the ones I'm showing you. Okay, I'm going to start with the not so sneaky ones and then go all the way to the sneakiest ones. Because when you are, so say the scenario is you're an adversary, you compromise a machine, and from that machine, you want to figure out what else is in that network. Now, if you do the naive thing, you'll basically scan, brute force the entire network, and that is very noisy. And so the first thing, that describes the first kind of scan, and this is the TCP open scan, which you can get when you do nmap-st or nmap-s. And the idea of this scan is to attempt a full three-way handshake on every single IP address and every single port that you're connected to. So that's the open scan, or whatever CIDR prefix you're scanning. Yep.
So the idea behind that is to make more noise, but you'll get more information.
Yeah, you can get exact information as to whether or not that server is up or down. And you can get some detail based on the protocol interaction. You can actually identify that server if you actually keep on with that connection. So if you do an open scan and you actually try and do the protocol handler associated with that, you might be able to get the version number. And we'll talk about this when we talk about operating system and server software fingerprinting. Nmap can be used to identify the version and the operating system, the version of the software, like the Apache version, and then the version of the operating system that you're running, if it has more detailed scans. And you would have to do basically an open scan to do some of that stuff. So this is a full connection. So you're basically doing the three-way handshake. You're attempting it against every single target. So you do a SYN, target responds with a SYN-ACK, and then you respond with an ACK. And then if all of this works, you have a connection to the target. Now, the issue here is that the target knows exactly how it got scanned and the person who scanned it, assuming that the thing hasn't been spoofed. If it's been spoofed, then maybe it doesn't. But like the target's like, okay, I know this is the IP address of the scanner because I have this connection tuple from that. So this is noisy. The other, so that's if it's open. If you attempt a three-way handshake, a connection establishment sequence on a port that doesn't have a server listening, the TCP implementation tells you to send a reset segment. If you get an unexpected segment on a port that's closed, the RFC says send a reset, saying this connection should not continue. on the target. So this allows you to determine whether a service is running or not right here. Moreover, if you don't get any response, what do you think that indicates?
Firewall.
Yep, the firewall. The traffic is being filtered. It never reaches the destination. So immediately with this open scan, you get a lot of information, open, closed, and whether or not it's filtered. We'll see that some of these other scans might only give you, it's either open or filtered versus closed and other things. But here you get all three. Okay, so you get no response if that thing is filtered by the firewall, but here the target knows who has scanned it. This leads to a stealthier option. This is the half open scan. And the port closed and the traffic filter is the same. But when you do this three-way handshake, if you get a SYNAC, you can immediately stop as an attacker, and you can send a reset connection. And what happens is that the operating system will delete this connection attempt without notifying the actual server software. It will not show up in like web server logs, for example. Now, the operating system sees that this thing has been established, this connection attempt has started and then aborted, but unless the operating system is logging that failure, it just basically disappears. You don't, like, the adversary can do this scan without showing up in a log file. Okay, so this is stealthy to the application, but if you know people are doing half open scans, then in the operating system, you can basically do some logging to try and reveal that this is being done. Here's another one that's even stealthier. Send a random TCP acknowledgement to a port. And what happens here, when you send an unexpected TCP segment to an open port, what you'll get back is that reset, right? You get an unexpected segment, and if you're in a connection that's a listening connection and you get this unexpected segment, the target's going to be like, oh, that's bogus. I'm going to reset this connection if I'm up. And that's part of the state machine. That's encoded in the state machine for TCP. Yep.
For the stealth scan, are there any drawbacks to doing that as opposed to the open scan? Like, why would you use open scan?
If you actually wanted to do some interaction with the target to do some more a deeper scan. So Nmap has these flags for doing deep scans. And then if you turn on one of those deep scans, by default, I think you're doing an open scan first. And then when you connect in, you're running some heuristics to figure out. You actually do need a real connection to do a deeper scan on some of these.
That'd be like the script flag.
Yeah, these would be all flags. These are all flags. You see all the flags I'm giving you? Like if you look at the man page for Nmap, I mean, you'll cry with the number of options that are there. You pretty much have to Google what you want the tool to do and then find the flag. There is no way you're going to memorize all these flags. Yeah, maybe you'll memorize what the first part of this flag is, like the -s, and maybe you'll memorize some of the common ones, but like there's just too many. Programmatically, there's so many different ways to do a scan that it's making this so that you can get access to that, but then there's basically so many flags to configure that behavior.
Yeah, we just at RainSec last month met a guy that said he took an 80-hour course on Nmap.
80-hour course on Nmap, yeah.
It's like a
Yeah, and like all of this stuff in this class, this is like the first maybe foot, but like it goes deep. Like there's stuff that goes really deep. And so this is why it's important to just like, well, what did I like in this course? And then maybe I'll specialize in that first, because there's just too much. It's like boiling an ocean if you're trying to learn all of it all at the same time. Okay, so even stealthier is this other scan where you just send a bogus ACK to a port. And if the host is up, if it's listening on that port, then it'll just reset that connection. It's like, hey, you know what? This I should not have gotten this. I'm going to just reset your connection. Okay. You get no response if the host is either down or filtered. So unlike the previous one where you can just disambiguate those two, In this case, if the host is down and you get a random ACK, nothing happens. And then if it's filtered, nothing happens. So yeah, stealthier, but you get a little bit less information on this side. Okay, similar to the ACK ping are the Christmas scan, the fin scan, and the null scan. And these came out of just reading the RFC for TCP and seeing this part. It says segments with unexpected out-of-state flags on an open port are just dropped. And so TCP ports that are listening expect a SYN or an ACK. If you send a packet to a closed port, you get a reset response. But if it's out of state and it's open, it'll just be dropped. So this allows you to then do all three of these scans. So the first one I'm going to talk about is the Christmas scan. And it's called the Christmas scan because you light up the flags in the TCP header like a Christmas tree. So the fin, the push, and the urgent flags are set. And then you point this thing at a server or target. And if the thing is open and it's got all of these unexpected flags set, it's just going to drop the packet. Now, because firewalls also drop packets, now the fact that you get no response means that it could be either up or filtered. Okay, so this is why it's important to understand your output. And Nmap will actually tell you, hey, with this set of flags, it's either open/filtered or closed in this case. So Nmap will helpfully tell you what you can make of the results that it's giving you. Yes.
So both the Christmas tree scan and just the packet scan, the PA, are both for stealth reasons.
Yeah, all of this stuff is for stealth now.
So if you don't know what they're scanning for, you're gonna if you try one stealthy approach, but it's not stealthy, then it seems like you have a second chance.
Yeah, so yeah, if you think it's stealthy, but someone has put a sensor in there that detects that, then this is where the tables have turned. The adversary is at a disadvantage because the adversary doesn't know that you have some of these other detectors in here. Like, for example, if you send a Christmas scan, like this is a well-known Nmap scan. And so the fact that anybody has sent this packet should indicate malicious activity, right? And so you have to be looking for it. Like the defenders have to be looking for it, but as soon as they see it, they're like, all right, that machine or wherever that packet came from, assuming it wasn't spoofed, that machine's got a problem. So this is a cat and mouse thing. And as it turns out, if you are building your tripwires well enough, then the adversary is at a disadvantage when they come into your environment and try and do any kind of discovery operation. Okay. So the closed port is going to send back the reset in this case. So that is your differentiator in this particular scan. Now you can simply do a fin scan and get the exact same thing. So if I just set the fin, so say someone is basically monitoring these things, you could just send the fin. And this is fairly common that you would get a fin packet going back and forth. And then you would get the same behavior. If it's filtered and unexpected, or if the host is up and unexpected, or if it's filtered, you get nothing. And then if it's down, you'll get that reset. The null scan is also similar. Again, out of state, you don't have any flags set. No SYN, no ACK, none of the other flags. And then you basically get the same thing. It's dropped if it's filtered or the host is up, and then the reset if it's down. Okay. So not all TCP implementations will do this though. So like you're writing software to spec and sometimes you make a mistake, or sometimes you're like, meh, I'm going to ignore that part of the RFC because that'll never happen and I won't implement it. And this happens. Your TCP implementation is not well, with everyone running Linux, maybe it's more uniform, but it is the case that your response to these scans might differ based on the TCP stack you're actually running. And because all of these things are imperfect, variations in the responses can point out which operating system you're running. And so I said earlier that you need to do a full connection scan to figure out like the server software and the operating system you're running. But if you can do a scan like this, and if only one particular operating system behaves in an abnormal way, then you can actually fingerprint the operating system just from a TCP scan rather than doing a full connection. And this is one of the heuristics that that ends up being built in to the Nmap operating system detection flag. So the -O is trying to, when you point this at a machine, it's actually trying to figure out what implementation is running on there. And that's really valuable information. If you know exactly the version of the software and the operating system, all you have to do is say, hey, Google, what are the vulnerabilities associated with that particular version? Right. And then your job as an adversary is much easier. You're like, okay, I know what to send these folks. Yeah.
As an adversary, whether or not you use Nmap, would that be dependent on their security? Like,
Yeah. So the other thing is, how do I get Nmap onto the victim machine? And what happens if the defenders are actually looking for me to download and install this? And so you would have to, there's this idea, we'll cover this next week, this living off the land binary, where maybe I can find another program that's been blessed on that machine to send my scanning packets. So yeah, that's, yeah, how do you get Nmap on the target? Well, sometimes the payload, the malware payload will download that tool. Will download the Cobalt Strike or the Metasploit, whatever Metasploit interpreter or whatever that second stage payload that allow you to do the scanning. So some of the scanning stuff is actually built into other, like, so I don't think we have a Metasploit lab in this particular class, but that they also, you can scan from that tool as well, and it'll do something similar. Okay. So that leads us to the stealthiest scan of them all. At least that's me, actually, not anyone that yeah, according to me, this is the stealthiest scan of them all. This is the idle scan. And the idea of this is to use a deputy to scan the machine so that you don't have to give up your identity as the person performing the scan. So how does this work? The first is you have to find a zombie willing, well, a zombie that can basically act as your deputy. And any machine that's up on the network is fine. And so what this idle scan is doing, there is this IP identifier number used for fragmentation. I don't know if you recall last week, I talked about the IP header, and there's a set of fields for fragmentation. Now, as part of that row of fields is an identifier, so that when you take a big packet and you break it up into multiple fragments, they share the same identifier so that the recipient can put those fragments together and regenerate the original IP packet. And so that identifier is basically the way IP is implemented. It's a number that sequentially increases on every new IP packet that the machine sends. Okay, so this works on an idle machine where, and this is what this zombie is. Say this zombie doesn't really have any connections. And then what the adversary does is like, oh, I'm going to find what is the identifier you're using. So I'm going to send a SYNAC to a closed port, and then you're going to respond with a reset segment that will reveal in your IP header the identifier you're currently using. Now, if I did this again, that identifier would be X+1 instead of, like, if the adversary was to do that again. So the first step is to figure out what the identifier currently is. The second step is to spoof a TCP SYN packet with the source of the zombie, of the idle machine. And by doing so, the target is going to send the SYNAC back to the zombie. And the zombie's like, hey, I never sent this connection, reset this connection. And by resetting this connection, it's going to reset the connection by with an IP packet that has this ID incremented by 1. Okay. Then the adversary is going to check the IP ID again. And if the reset happens with X+2, then it knows that that port that this SYNAC happened. So this is like a way of detecting that there's an open port here, because the SYNAC occurred, and then you reset this thing. If it didn't, if this thing was filtered and was down, then this SYNAC and reset would not have been sent. And then this interaction would have had the IP ID of X+1 instead of X+2. Yeah. Yeah, very sneaky. So, but this is where knowing your tools matters, because this is hard to detect. And when it is detected, you're basically blaming the zombie, unless the zombie is keeping logs on this, which is like no one's keeping these logs. I mean, basically, so some companies, they have network flight recorders. They're logging all the packets, and then they would have to basically at the back end do some kind of querying to see, how did this scan happen? Where did it come from? And this is all part of forensic analysis, but this is the kind of stuff you would have to look for on a post-mortem in order to figure out where the adversary was. So yeah, this is the stealthiest one. Okay, any questions?
Do we have a network forensics class?
No, we don't. Yeah, there's a company that wanted us to start one up. Forget the company name. But then we were like, yeah, you could give us some of the curriculum, and then we might try and offer it, but yeah, we don't. But actually, Kevin might be doing a computer forensics class that has networking. So I guess that we'll do a little bit of forensics with packet traces. So that's one of the things you would do at the network level. You would use packet traces to try and do some querying. And so if you sent your packet data to a backend data warehouse and then allowed some querying, you might be able to do some querying that will reveal this kind of information. Okay.
Counterintelligence kind of, you have your own like backend thing, the querying the scanner.
If you're keeping logs, so I'll talk about this later. There are these SIEMs, the security incident and event management backends. They're collecting everything. And so when you have a compromise, you have this large data warehouse with all the security related events in it. And then hopefully you can do a sort of a forensic analysis that would trace you all the way back. I don't know if something like this idle scan would, but the adversary is in your network potentially. So maybe by launching this particular piece of malware on that machine, that'll leave a trace in your basically backend audit log. All right, I am going to go up a layer in the protocol stack and talk about application layer security. Obviously, if it's application layer, you're expecting a whole bunch of HTTP, which I'm not going to cover because we have a separate web and cloud security course next winter, in fact. But I am going to cover a little bit of HTTP when we cover cookies in the privacy section of this class at the very end of the course, because knowing how cookies work is important for understanding privacy concerns at the application layer. I am going to talk about DNS, though, the domain name system. So I'm going to first talk a little bit about how it's architected, and then talk about how it can be exploited. So the first thing is naming protocols. And in general, machines like internet hosts and routers like to use fixed length addresses or numbers. So the hardware address, the IP address, those are better for machines to parse and handle. But humans don't like that at all. We don't like memorizing numbers. We like mnemonics that are variable length. We like names. So the domain name, so the domain name format that you see here, or you could have keywords, which is something that AOL did back in the 80s, to basically say, if you type in Super Bowl, I have the exact site for you on my service. That's a keyword protocol, naming protocol. And so DNS keywords and other naming protocols are basically mapping a name, a variable length name, to a fixed length address. So the dominant naming protocol that we have today is via the domain name system. And this was done in 1984, or 1985, soon after the internet protocols were pushed out. This is an application layer protocol that is used to resolve variable length names. It is TCP or UDP port 53. So if you have a packet that's going to this destination port, it's a name lookup packet. And it's just going to take that name and give you an IP address that results from the resolution of that name. And it's an interesting architecture because this naming protocol is core to the internet, but it's implemented at the application layer. And this is this is compatible with the internet design of having a really dumb network and pushing all the complexity out to the edges on an end-to-end basis. Okay, so this is a look at the DNS protocol, and the messages that get sent back and forth between a client and the server use the exact same format. So there isn't a request format and a response format. It's all the same format. And in this format, there's an identification number that uniquely identifies a request-response pair, a set of flags that control whether it's a query or a response, whether the response is authoritative, and then a number of questions, a number of answers, a number of authority records, and a number of additional records, where this is going to describe what is attached in this payload. And so these 4 sections follow the question section, the answer, the authority, and the additional information. So again, the query is sent with the request flag and then some questions to ask. And then the responses are typically also specifying replies, and then with any number of these answers, authorities, or additional information as the response. Okay, so this is what it looks like. I have a client, and then I have a DNS server that it's trying to communicate with. The first thing that happens is that the client creates this query with a message ID. And so this is the DNS ID field, and say it's 12345. And then I am asking this DNS server, what's the address of cs.pdx.edu? And then this is going to get encapsulated in a TCP packet or UDP packet, destination port 53. Client port can be anything. And then in IP, and let's say this client is going to ask this DNS server what this resolution is. It's going to say from client IP to, I don't know why these are reversed, but like to this DNS server. And that's what gets sent across to the local DNS server. And then the DNS server will resolve this name. And then assuming that it has a mapping, it basically creates a response using this same DNS ID so that the client can match the response to the request that it had sent. Say cs.pdx.edu is 1.2.3.4, sends that back to the client using this same connection. Okay, so the question you should be asking yourself as you're looking at this protocol is, what about confidentiality, integrity, and availability in this thing? Do you think this has been addressed properly with this protocol? Because that's basically the rest of this class. This is all sorts of stuff. Yeah, this is not encrypted, source integrity via this ID number right here. So that should remind you of the connection level integrity of TCP. That's basically how DNS is doing integrity. Okay, so before I get too deeply into the attacks, I'm going to talk a little bit about the record types in DNS. DNS is a distributed database, and the records that it stores in its databases can have many different kinds of types. And so this is referred to as a resource record. And the resource record format has the name of the DNS name, or the name that you're looking up, its value, a type field indicating the kind of record it is, and then a TTL that says this is how long this record will be good for when I resolve this for a client. The most common record type is the A record. Just give me the address of this name. And then the value is the IP address, or a list of IP addresses if you want to be fault tolerant. If you want, like, say you have like 6 IP addresses that map to that one name, and then one of the 6 goes down, well, you still have the other 5 that the client will try and connect to if that one that it tries is down. Now, to support IPv6, there is a quad A record. that you could actually store as well, which is the IPv6 address that a particular name resolves to. And for most of our machines in the particle lab, you can do a lookup or a AAA lookup, because most of these things are running IPv6 as well. If you wanted to connect up to the IPv6 version interface rather than the IPv4, just for fun. There's another kind that's common. It's the MX record. And this is the IP address of the mail exchanger for that domain. And so, for example, if you go to www.google.com or just google.com on your web browser, that goes to a different IP address than if you sent an email to someone at google.com, because there are separate records in the database for each one of those kinds of services. So if you have a domain, an email domain, foo.com, the value is the mail server associated with that name to connect up to send email to, in this case. There is a format of record for aliases. So if you want two names to map into the same entry, then you can create this CNAME alias and says, hey, I'm going to point this name www.ibm.com to server east backup to.ibm.com. And so the name and the value, in this case, rather than being an IP address, this is another canonical name as the value. The next one is a critical one. This is the NS record. This is the authoritative name server for the name you're looking up. And so if you are, and this is actually implementing the branches of the hierarchy in DNS, as we'll see later. Well, the name is the name you're looking up, foo.com. The value is the host name of someone who might know this name, rather than actually being the IP address itself. So if you query a DNS server looking for foo.com, and that DNS server doesn't know what that address is, but it knows the person who might know what that address is, that's the NS record. Okay. The next one, which will become important when we talk about email, is the text record. And this is a mechanism for publishing data on your domain. So it's done on Google. This is done to verify that you own the domain. So if you have a website and you're trying to use your domain and point it to it, and you're trying to host things on Google, they'll say, well, show me that you own that domain by putting this record in the DNS system. And then when it queries the DNS system, it'll see that you have published that piece of data that it asked you to. And it's like, okay, you own that domain. So it's kind of used for authentication that you own a particular domain. And that's through this text record. And then, as we'll see, this is critical in implementing SPF and DKIM, which are ways of protecting against email spoofing. And this will come later when we talk about email. Okay, so the DNS canonical namespace is done as a hierarchy. And so this is familiar to you. It's got different subdomains as part of this hierarchy. And this maps from the right to the left to the hierarchy of servers that will be used to resolve these domains. And so it starts at the root, and actually there's an implicit dot at the end of this name that you see here that people omit. But really, this specifies the root. And then from the root has pointers to all of the top-level domains that can precede the root. And so this is the root of the DNS hierarchy, and it points down to the TLD. And then from .edu, the .edu TLD has pointers to all of the subdomains that it knows about. So PDX, UCB, GWU, and then so on. So this is the way the DNS namespace is organized. And so when you want to query the DNS hierarchy, there are two parts on the client side. The first thing is a resolver on the host. So I have a machine, it needs to look up at a name. There is some software either in the browser or in the operating system that is going to know how to create a DNS request, a query. And then the other thing that is part of the client is a local DNS server that is going to be brought up to handle this query into the DNS hierarchy, which will show up on the right. So that's two parts that are local to the client. And so at Portland State, we have several local DNS servers on campus. You could also use Cloudflare's local DNS server 1.1.1.1, which is in the Piddock block downtown, or you can use Google's 8.8.8.8, which is in the Dalles. But it's basically some host on the internet that you can forward DNS requests to in order to get your names resolved. This local DNS server, you can set it manually, or you can use DHCP and get the entry that your DHCP server wants you to use. Okay, on the server side, there are this collection of root name servers. This is the top of the hierarchy. And if a local DNS server gets a query which it cannot answer, like say it doesn't have anything cached from prior lookups, then it will by default forward the query that you send it to the root server or one of the 13 root servers on the internet. The root server, if it can't respond with an authoritative answer, the root server is going to forward you to the top level domain servers. And then from there, you will then go and traverse this hierarchy down to the actual authoritative name server that serves the name that you're trying to get access to. So that's a picture of this. Other questions about the architecture of DNS? This is an animation of what goes on. I have a question, I send it to the resolver. Resolver sends it to the root. The root refers me to the .com. The .com refers me to the actual authoritative server. The authoritative server gives me the answer. The resolver sends it back to me. So yeah.
So do they use hashes, or what do they use to find like the CNAME or?
So the CNAME would be implemented all the way down here. And however you store your own local database, you could use a hash table if you wanted to, but like you're basically storing, because this is a distributed database, you are going all the way to the leaf of the hierarchy. And this leaf is, in this case, glucn.com is going to be able to issue any of the records for that domain. So this is what it means when you own that domain. You own the DNS server that will issue authoritative lookups for your domain, is the idea here. Okay. So yeah, just replay this animation and see these NS. So one of the things that's happening is the root server doesn't know the name, doesn't know this address. It only knows the authority for the .com name server. And so when this happens, where you're asking this name, the NS record for .com is what the root server sends back. Likewise, for .com, it's going to send you the NS for glucn.com. And that's why I mentioned those different records in that database, because you're asking for the A record, and it only can give you the NS records until the very final name server can actually give you the answer. And so this is an A record going all the way back to the client. Okay. You have another question? Yeah.
Yes, there's like a local DNS cache. Does your system implement that itself, or is there a DNS like?
It can be implemented in the local DNS server, which I'll get to next. So the DNS lookups are cached throughout the hierarchy. So in this case, Portland State would like you to use their own local DNS server so that it can cache lookups, right? It can also see all the domains you're visiting, but like, say it wants to do this for performance rather than to monitor students' activity, then what's going to happen is you're going to ask this local DNS server for a name, and then assuming this is a fresh server, doesn't have anything cached, it's going to perform this lookup and get the NS record for the root, the .edu, and then potentially the NS record for pdx.edu, and this is going to get cached because you don't want to have to look this up again and again and again. And so if these NS records have a TTL, then you will cache that record for that TTL value before you delete it. And then you can say, oh, I know the authority for pdx.edu. Can I ask this authority for www.cs.pdx.edu. And then this DNS server says, you know what? I don't have that A record, but I have the authority of the next subdomain down, and that's cs.pdx.edu's DNS server. And then when you ask, so this gets cached as well, right? So you're caching all of the lookups that you have done as part of the hierarchy. And then when I look up www.cs.pdx.edu, I get the authoritative record as the A record, and then I'll also cache that. So now these 3 records are in the local DNS server, so that when I do a subsequent lookup, say I want mashimaro.cs.pdx.edu, this local DNS server has the authority for cs.pdx.edu already. And so this will bypass the first 2, and we'll go straight to the authority for cs.pdx.edu and then get this Mashimaro address. And then Mashimaro will get cached here, and then the response will go back to the client. Okay, what happens if someone poisons the local DNS server with a bogus resolution? Say someone hijacked, maybe not Portland State's, because we do security right in this university. No, I'm just kidding. I think this is possible, where local DNS servers can get hijacked, or if the adversary is sitting around the local DNS server, the adversary can generate fake responses, right? We just talked about how DNS is doing security based on that DNS ID field, the authenticity. If it sees the local DNS server querying the hierarchy for certain names and IP addresses, it's just like, yeah, here's the answer. I know it. I know google.com, I know yahoo.com, I know every domain that you would ever want. And then I'm going to poison this local DNS server. And as soon as I poison this, and I'm going to make the TTL infinite, so that you're always going to get the same record, and then your resolution goes somewhere else. So that is a problem. This is called DNS cache poisoning. Okay, so I want to give you an example of the use of dig to query the names, the DNS names system. So this is a simulation of how the DNS lookup would work from your web browser or from the resolver or local DNS server as you query the hierarchy. The first thing I'm going to do is type dig by itself, and it'll give me the list of root servers. So that's the root of the query of the hierarchy that I'm going to query. And then it's going to give me these root servers, and I'm going to query the F root server. And from the F root server, I'm going to then do a query looking for this DNS name. And so if I dig at the root server, it's going to give me the NS record for the .com TLD. And then I'm going to query that for this name, and it's going to give me the NS record for this domain. And it turns out I host my name at Google Domains, and then I can actually go to the Google Domains name server and get the actual A record. So I'm just going to simulate this using the dig tool, just to show you what is going on when you do this operation. So I'm going to start with dig, and then you can see that this thing is the list of the 13 root servers. And then you would say, okay, well, what is the IP address of this root server? And you can see this is the IP address. So now I'm going to query this root server using a name. So I can say dig at 192.5.5.241, and then I'm going to look for this name. So the root server is not going to know this name, but it's going to tell me what the authority for .com is going to be. It's going to say, I'm going to just give you my next arc in the hierarchy. And then it's going to give you all the TLD servers for the .com domain. So you can see all of these things. You have a question?
Yeah, just about the dig with no arguments. What's that?
Dig without any. So every machine has the names of all the root servers. And so you need to bootstrap any DNS lookup. And so it's just going to give you, these are all the root servers. And then you can actually query. And the IP addresses are also included in most packages, because you need some way to bootstrap the query, the hierarchy.
So those are all the DNS The 13 DNS servers.
Yeah.
Oh, well.
Yeah, but they're actually way more than that, but they're hiding under 13 IP addresses. So like, it looks like 13 IP addresses, but like it's just like 1.1.1.1. It looks like one IP address, but it's actually thousands of machines all throughout the globe. This is the Anycast thing that I mentioned earlier in IP just briefly. So this is going to give me the NS record, or the records of all of the different TLD servers. So then what I'm going to do is I'm going to query the LTLD for the next part of this. And so this is the LTLD right here. So I'll do a dig at 192.41.162.30, and then it's going to give me the next part of the hierarchy. So it's going to give me, well, I don't know, I can't resolve that name, but I can send you to the authoritative servers who might know that name. And in this case, because I host this domain on Google, it's giving me the Google ones. And then I can just query Google. And in this case, I'm going to query this particular one. And then you'll see I get the A record. I get a C name as well. And then the A record, the answer section has the A record that gives me the actual IP address. Okay, so this is just a useful thing to know as you're doing some of your navigation and DNS intelligence on a domain. So now you know that this particular domain, I do all of my hosting for the DNS through Google. Yeah.
Is the authoritative name server here the same as the server hosting the banks.com?
No, it isn't, because you see this A record is a Portland state address. I told Google that I wanted it to run the authoritative name server. And so that's why the authoritative name server is this IP address and not anything at Portland State. So the web server is actually in my office. So it's a Portland State domain. If I wanted to be the authoritative name server myself, then I would register with the .com TLD that the authority for my domain is Mashimaru 131.252.220.66. And then when I traverse the hierarchy, it would go to that machine in my office rather than the Google domains. Okay.
Is that like bad security practice to have the same?
No, it's lazy. It's me being lazy. And I have to set a bind on my machine. And I have to like manage the database. And so like, yeah, and I have to do the patches. I have to update, like if someone, if there's a vulnerability in the name server software, I have to update it. So I'd like, forget it. Google does better operational security than I do. So I'll just use it. Okay, the other useful thing is reverse lookups. Given an IP address, it's really useful to find the name, the domain name that it's associated with. And that's done with a special record type called the pointer record type, which I didn't talk about earlier, but it's just one of those. The pointer record type works that so that if you have an IP address and you reverse it and you tack on this inaddr ARPA, what happens is that you'll be using the DNS hierarchy to figure out the domain name associated with that IP address. Now, this is because anytime you are given an allocation of IP addresses from a registry, you are required to set up these pointer records that will respond to reverse lookups. And when someone does an inaddr.arpa DNS query, then what happens is that these things will map to these regional internet registries that record all of the organizations who have set up pointer records that it has given IP addresses for. So this is done ahead of time. As you register your IP addresses, like Portland State registers 131.252. In order for them to get that block, it has to agree to support the reverse lookups on 131.252. And then it registers with Aaron or with Aaron to say, you know, when you get a inaddr ARPA query, forward it to my DNS server and I'll do the reverse lookup and give you the actual DNS name I have assigned to that IP address. Okay, so that's what, so I want to show you an example of this. I can. So one way to do this is to do a dig-x. And so what's happening here, this is going to Aaron. And then Aaron is like, oh, the people who own this IP address is Portland State. And then Aaron is going to forward this to Portland State. And then Portland State has this pointer record that says the name that we have assigned to that IP address is mashimaro.cs.pdx.edu. Yeah.
So Portland State controls all the 131.252 IP addresses.
Mm-hmm.
So in a way, they own 1/52,000th real estate of the internet.
Yep. Yeah, we own a Class B, so that's 65,000 addresses. Yeah, right. Yeah, 2 to the.
Because we got in on the internet when it was brand new.
Yeah.
So we got a lot of.
I don't know the history, but yeah, most large universities would have at least a Class B.
If you want the history, Jonica will tell you.
Yeah, Jonica is your guy. Yeah. So you can also query that in-ARPA address, asking for a pointer record, and that's what this one will do, and it'll get you the same thing. So that's really useful. If you have an IP address, you're like, well, where did this come from? When we talk about doing network intelligence and DNS intelligence, this is the kind of stuff you would be doing to try and trace the source of where this stuff is coming from. Okay, one of the things that doesn't show up is that if I point an alias at Portland State addresses, again, that doesn't show up in a reverse lookup. So all of this Oregon CTF stuff that I have running on my machine, it only shows you what the organization has assigned as a name to that machine. But if I control another domain and then I just point it to that IP address, there is no record of that, really. Unless you actually try hard to figure out what that is, I should say. Okay, let me continue here. All right, we already did that. So now let's talk about DNS attacks. The first attack I want to talk about, we talked a little bit about poisoning, but I'm going to get to it in more detail later. The first attack I want to talk about is this thing called rebinding attack. And one of the things to note with web browser security is that the security model of the web is tightly bound to DNS names. We allow certain things based on the name of the resource, the name of the URL, the host name in the URL. Things like cookies, things like content security policy. When we talk about the web's same origin policy, which you'll come across, that's all done based on the name of the web server that you're contacting. Cross-origin resource sharing is done this way. The same origin policy is done this way for controlling which scripts from the internet your browser is going to execute. So all of this stuff is done by the name. The problem is that the adversary can control the names and tamper with the bindings of DNS to basically subvert any of these security policies that are underneath. And so rebinding is just one of these. So here's an example animation that I want you to, I'm going to try and explain in real time. The problem with this animation is I can't stop it. Actually, let me try and restart it. So what's going to happen is the attacker is going to issue a DNS name with a tiny TTL. And then it's going to trick you to visit that domain. It's going to trick you to visit the domain, and that domain's got a tiny TTL. It's going to deliver you some JavaScript that points right back to its domain. But because that TTL is so short, you're going to have to resolve that name again. And when you resolve that name again, the adversary is going to trick you into going somewhere else. And in particular, a local private machine on your network or a local service on your network. And you're thinking you're running a script on this attacker domain, but you're actually running it against your own resources. And that's what this rebinding attack is going to do. Okay, so now with that, I'm going to play this animation and hopefully it'll make a little bit of sense. So the first thing is resolving the name, and then the TTL is super short. And then I'm going to fetch the page, and the page is going to come back with some JavaScript, and that JavaScript, the name is going to expire, and that JavaScript, rather than going back to the web server, is going to go back to this internal service. And this internal service is going to, this is something that you want to protect. And so this JavaScript is the browser is going to say, oh, you're still going to this web server, when in fact, it's attacking an internal service that you're running. And this internal service could be a server listening on localhost. Remember when we said your localhost's listening is meant for things that you don't want public people to access? If you do this rebinding attack, the browser is thinking it's going externally, but it's actually connecting up to a local service, and you're revealing what that localhost service is exposing you. So this is a problem because a lot of these crypto wallets, the way they were built was to run some web server, some JSON RPC service, have it listen on localhost, and assume that you have to be on the machine in order for you to access your crypto wallet, right? And if you allow unauthenticated access to your local crypto wallet, then what the adversary is going to do is it's going to deliver you a malicious script, rebind the address of that script so that it hits your internal service, and then as part of the script, send your private wallet keys somewhere else. Okay. Yep.
How does it know where your internal service is?
It would have to brute force that. So if it's a crypto wallet that's well known, then it would be like a particular port on localhost. So the wallets, when you install a crypto wallet, they have well-known ports that they listen on, and that JSON RPC port, it's like 3303 is one of them. But like, yeah, all the blockchain, all the cryptocurrency stuff is trying to use a particular set of ports.
So these services are set up already, so they know if they send it through this port, it'll go to that.
Yeah, and if you happen to be a victim that doesn't run a crypto wallet, this will just fail, and then the attacker will move on. But you know, the attacker site would be like, hey, get rich quick on Ethereum. And then of course, people who want to get rich quick on Ethereum probably have a wallet running on their computer. And so they would hit that site and then the private key of that wallet. If this interface is using unauthenticated JSON RPC, or if the user has opened up this wallet temporarily, because like if you want to use the wallet, you have to unlock the wallet in this RPC. And so if you just happen to catch a user after unlocking the wallet, and then this malicious JavaScript accesses the wallet, then you could get this thing to reveal its keys or to sign a transaction that it didn't mean to sign, is more typical on this thing. Okay. Yep.
So it seems like the hard part about this would be the attacker would need to make a site that's legit enough the person would want to go back to it.
Yep. So you have to have a good lure on this, and the good attackers are pretty good at lures, especially if this get rich. I mean, there's people who want to get rich quick are going to click on that thing. They want to get rich in a hurry, and then they'll get poor in a hurry.
Terrible irony.
Yeah. All right. The next attack is this cache poisoning attack. Because there's minimal authentication being done on the responses, you have a problem with integrity. So there are a lot of ways of doing this cache poisoning. The adversary can attack the DNS servers directly. The adversary can also, on the client side, do a person in the middle attack, like a rogue access point, perhaps, and then be in the middle of your DNS queries. Could do the ARP spoofing thing, as we saw earlier, to be in the middle, or can just spoof DNS responses right on the network to modify those things. And if you're doing this in the clear, which most people are, you can easily craft those responses before the resolution actually takes place. So this is a cartoon I like that was I forget where, I think this is Mozilla, came from Mozilla. You basically have to protect everything here in red from attack if you want to prevent DNS cache poisoning. And this is hard to do, right? You don't get to control all of this is the problem. And so I'm going to go through different animations that show you what the adversary can do. The first one is to sit there on the wireless network or on the local area network to monitor queries going to the resolver or the local DNS server, and then just to send a response back before the resolver even finishes resolving the name. And in this way, the client's like, oh, sweet, I have a fast DNS resolver. I'm getting this answer so fast. It's incredible. Like the IT, Jonica is doing an awesome job with DNS servers because I'm getting this thing immediately after I send it. And it's because the attacker is just telling you, go to me for everything is the idea here. Okay. The other way to do this is to hijack communication from the resolver to the hierarchy. So again, if this is in the local DNS server for Portland State, then what you would do is you would, say you're in their data center, so the OIT machines are right over here, you would connect up to this, and you would monitor any queries going into and out of that resolver. And as soon as you saw this resolver attempting to query the hierarchy, you would poison the resolver's entry. Because if you're in this one, you're only impacting one client. But if you're hitting the resolver, then this thing is going to get cached, and then everybody at Portland State that's using this particular local DNS server or resolver gets that bogus entry. So that's another, this is another scenario where you're just spoofing I don't even know what that, ovhcloud.com is what you're trying to hijack there. Okay. The third way is to hijack the traffic at the authoritative server. So if you are in particular trying to target this authoritative server right here, then on this lookup, this is where you would race if you're on this network, then the adversary would just take all of those resolutions and point the users trying to resolve that name to somewhere else. Yeah.
What's the highest known incidence of DNS poisoning?
Highest known incident of DNS. Oh, people attack the root server. Yeah. Yeah. This is everywhere. Like you could potentially pull this off everywhere. Yeah. Poisoning and hijacking can be done anywhere throughout the hierarchy.
So on your browser, like the Firefox, somebody clicks on everything, does it still show your URL like google.com, even though you're pointed at?
Aha. So that certificate is what's going to protect you potentially, unless someone has managed to forge the certificate. So this will get us to myetherwallet.com, hijacked in 2018. This is the fourth way. Hijack the routes going to the DNS servers. Actually, this is not the authoritative servers. This is the DNS servers. I'll fix that later. This is a mistake. So basically, this is how it worked. MyEtherWallet is using AWS Route 53 to provide DNS. It's just like I am using Google for my DNS. MyEtherWallet's like, you know what? I don't want to run my DNS server. I'm going to have AWS run it. Like their operational security is way better than mine, and rightly so. This is actually good. This is a good deployment. You're like, yeah, they're doing it right. The problem with this is that we talked earlier how a more specific route that's being advertised on BGP is the preferred route that traffic will take. And so what happened was somebody broke into an ISP in, where was this? Columbus. Someone broke into eNet in Columbus and started to advertise more specific routes to the AWS Route 53 servers that were serving MyEtherWallet. And you can see these /24s being advertised that are right out of the Route 53 infrastructure blocks. Okay, so that's what happened. and then put up some fake DNS servers, and then redirected all of the lookups for my Ether wallet to some fake web servers in Russia, and then was able to pop up a fake My Ether wallet site and then get the credentials of users on the legitimate My Ether wallet site. And then they could go back and log in as that user and empty the wallets out of that site. Okay. This attack, if they were going to do it right, they should have not only done the hijacking, they should have issued themselves a TLS certificate, because what you said earlier, when you type it into your address bar, it's going to say, hey, there's a certificate. There's something wrong with the certificate. It's not, it's HTTPS, doesn't have a valid certificate. But if you hijack the IP address and you control the name, you hijack the DNS name and you have the IP address, you can issue yourself a certificate with Let's Encrypt, because that's the only thing Let's Encrypt will validate to issue you a signed certificate. If they would have done that, then it would have been impossible to tell. Unless you actually look and see, when was this certificate issued? And it was just issued like an hour ago, then you're like, maybe I shouldn't trust that certificate, would be your only option. But who does that? Who's checking the certificates of sites that they visit? Okay. This, earlier in the year, this is what happened. They did the hijacking and they got the certificate. And I mentioned this earlier in this class. This is the seller network bridge attack. They did the BGP route hijacking and they got the certificate issued because they owned that IP address range for a little while. And then this is where they could wipe out that particular bridge. There's a cryptocurrency bridge. And this is why you should not invest in cryptocurrency. Is my, at least like, this is why I'm not. I don't know, maybe you can, but.
Someone just lost $3.6 billion in Bitcoin. Because they had it on USB sticks in a coffee can, and they called the police to help them find it.
Oh, wow.
They just got all their Bitcoin confiscated.
Oh, right. Yeah, especially if that key is for a wallet that's illicit, tied to illicit activity.
Yeah, it's from the Silk Road.
Silk Road. Oh, yeah. Yeah, so that's one of the reasons why Bitcoin hasn't been banned, is that it's actually a good tool for law enforcement to identify criminal activity. Okay, so this is an animation of what happened that I really like. This is the way it should work. Like, you're asking your local DNS server, what is myetherwallet.com? The local DNS server is querying the hierarchy, figures out the authoritative servers are at Amazon. It says, hey, Route 53, what is etherwallet.com? Amazon says it's this address, 54.192. Client's like, oh, cool. Let me go to that IP address. And it goes to this IP address, and myetherwallet.com, the legitimate one, is there. It's got the certificate set up. You send in your username and password. It's all fine and good. This is the hijacked operation. The resolver's asking again. And then because of the BGP route hijacking, rather than going to the real Amazon, this thing is going to some other IP address, and this is where the adversary has set up a server to pretend to be Route 53, but the traffic is being sent this way instead of the legitimate site. And then says, oh, you know what? It's this adversarial IP address, and they're using a local IP address, but it's a global one that just happens to map to their fake version. And so their fake version of the site, they screen scrape the site, they make it look legit, ask for the username and password. The legitimate site never sees this login, and then the credentials are captured. Okay. The countermeasure. This is where DNSSEC is intending to address. So the DNSSEC approach is to do something similar to TLS, where you have authorities, you have the root server is your authority, and it's got signing keys, and it's going to start to sign certificates for the level of the hierarchy below it. And then those servers are going to have certificates that will sign the level before it. You're adding signing keys and certificates up and down the hierarchy to authenticate, to do source integrity of the lookup. You're going to do the exact same lookup, but it's going to be associated with signing keys and signatures that allow you to validate all the way up to the root that there is a chain of trust from the top to the bottom. We talked about this in TLS. We have certificate authorities that are signing certificates for websites. So it's like basically like 2 levels. DNSSEC is similar, but it's multi-level in this case. Okay. So you start with the root servers generating a public key, private key pair, and they publish their public key. And then what happens is that the TLD servers are going to ask, they're going to generate their own public-private key pair, and they're going to ask the root server to sign it. And so this is where the trust gets established, because only a certain, this relationship has to be done probably as an out-of-band thing at this level. And then so the root server is going to use the signing key, their signing key, to sign the key for the TLD. Then the authoritative name servers will also want to get their key signed by a TLD server, right? And so you're basically having the root server sign the TLD server signing the authoritative name server, so that if someone is going to inject a bogus entry in this chain, you'll see that it's not going to be signed by the appropriate people potentially. Okay. And then when a user goes and does this resolution, not only are the records sent back, but the signatures of those records are sent back. And of course, the local DNS resolver and the DNS cache, they would know the public keys of the root server. And hopefully that associated private key is kept secure, and then they can validate it all the way down the chain. And so the browser is then going to verify that chain of trust all the way down. So this is the operation. I get a key and I query the root server. It's got a signature. I validate this. I get the key of the .com server, and then I query the name, get a response, and I validate the signature with that key. And I do the same thing. I get a key, and then I get the question, and then I have the signature, and I verify it, and then I get the answer. And all of these steps are now authenticated. Okay, I have 1 minute left. You don't want to set this up yourself. This is why I use Google for my DNS. I'm like, hey, look, there's a single button. All I have to do is click this button to enable and disable DNS for my domain. Let me do that. That's what I do. And that's why I don't run my authoritative server. And so this thing is now being pushed out. I mean, this is actually a tiny fraction of the domains that are out there, but more people are using this than not.